Hi, and welcome to the third topic of our Unit 9 Remediation series, where we'll be looking at chemical changes and tracking the progress of a reaction using potential energy diagrams. We'll look specifically at how these diagrams show the transformation of reactants into products in terms of effect of collisions and how energy is either absorbed or released, and the chemical vocabulary that's associated with those changes. So let's start by looking at this particular reaction that I took off of table I. I want to be able to draw and label its potential energy diagram, but I know the main shape is going to be dictated by whether this reaction is endothermic or exothermic. And in order to figure that out, I need to know whether it has a positive or negative value for its heat of reaction. So looking at table I, what I see is that this equation is represented right here. And under delta H, or heat of reaction, it tells me that it's negative 556 kilojoules. So for this reaction, delta H, the heat of reaction, is negative 566 kilojoules. That makes it exothermic, which means heat is released as a result of reacting carbon monoxide together with oxygen. So the way I can represent that in my equation is by making heat a product. Now, think carefully about this. Negative heat doesn't make a whole lot of sense. Heat is produced. How much heat? 566 kilojoules. So I'm going to add 566 kilojoules as a product of this reaction. And from here, we're going to be able to draw the potential energy diagram that shows and tracks this change over time. So on my y-axis, I'm going to track changes in potential energy, while along the x-axis, I'll just be looking at the progress of reaction. Where are we in terms of turning reactants into products? I'll start off with my potential energy of my reactants, just putting it somewhere on the diagram to show that yes, carbon monoxide and oxygen do contain a certain amount of energy. And I know that because this reaction is exothermic, heat is going to be given off. That's a decrease in energy of the chemicals themselves. So I'm going to end lower than I started. How these two values are connected is what tells us about the collisions and energy changes that are happening in this change from the potential energy of the reactants to the potential energy of the products. If I think about carbon monoxide and oxygen, if I just throw them together, we aren't guaranteed to have them react. There has to be collisions with enough energy and the proper orientation to make them change into carbon dioxide. So every single reaction, regardless of whether it's endothermic or exothermic, is going to require a certain amount of energy to get started. Once that amount of energy has been put in, our molecules bouncing around in our system are going to have the opportunity to start reforming bonds in new ways to create new molecules. That process gives off a bunch of heat until we reach the potential energy of the products themselves. Hence the sort of upside down smiley face or sad face of the middle part of every potential energy diagram. So what I'd like to do at this point is label all those values and sort of talk about what they're called chemically. So the amount of energy that I had to add into this reaction is called the activation energy. When you activate something, you get it started. So how much energy did this reaction require to get started? And if you notice, I didn't draw it from the very bottom of the diagram all the way up to this highest point because I already had a certain amount of energy here contained within the bonds of my reactants. Breaking those bonds holding my reactant molecules together requires energy. Remember, you can't break a pencil without putting energy in. In the same way, you can't break a chemical bond without adding energy. Therefore, every diagram is going to start off with a certain hill that you have to climb. That represents the energy that we need to put in, or the activation energy of the reaction. As we fall down this hill, we eventually end at the potential energy of the products. I know how much heat must have been released as a result of this reaction, just looking at the difference in the energy I started with and the energy I ended with. We know that this space this height, represents the heat of reaction. And we know from table I that this value is negative because it's an exothermic reaction. In order to get that negative value, what I must be looking at is where I ended minus where I started. A small value minus a large value will give me a negative result. So for exothermic reactions, what we see is this change in energy, change being final minus initial, gives us a negative result. So our heat of reaction is represented by this space, and it's equivalent to the potential energy of our products minus the potential energy of our reactants. So that is what gives us our negative value. There's not much else that we can label here on this diagram. You may see sometimes this high point being called the activated complex. That will really only show up in maybe one Regents question out of a million, but you know that the activated complex must be what the activation energy led to. The only other thing on this potential energy diagram that's of interest is what happens when I add a catalyst into this reaction. You guys know that catalysts make reactions go faster, and the way they work is not by changing the reactants or the products, but by changing how easy it is to interconvert from one to another. So what catalysts do is that they bring the reactant molecules closer together and decrease the amount of energy that you need to put in to get the reaction started. Remember that we call that amount of energy the activation energy. So a catalyst decreases the activation energy required for a reaction to take place. So looking at this is all the stuff that we need to know about a potential energy diagram. And you can imagine the same things apply whether you have an exothermic reaction like this one or an endothermic reaction where delta H is a positive value. So pause the video for a moment, draw a potential energy diagram for an endothermic change, and let's come back and sort of revisit where all these different values would be on that diagram. Right, hopefully you've had a chance to draw that endothermic potential energy diagram. I just picked a random equation from table I that I saw was an endothermic chemical change. So for this one, it was a positive 182 kilojoules reported as the delta H value. So I just picked that to sort of guide my thinking. And the potential energy diagram that I drew looked something like this, where we had to increase the energy going from reactants to products, indicating a positive delta H value. So here on this diagram, all things remain in the same place. The activation energy required to break the bonds of the reactants, because energy had to be put in, goes from my reactants all the way up to my activated complex, activation energy. Notice that the activation energy for an endothermic reaction is typically much higher than that of an exothermic reaction, just because of the relative placement of reactants and products. Again, my delta H value represents the distance between our products and reactants. And because that is a positive value, we want to do big minus small, so we subtract where we ended from where we started to get that positive value for delta H. So at this point, take a look at the questions provided on the playlist and consider what you know and what you're still working on for potential energy diagrams and reaction progress.